You're and you're muted.
Yeah, I just realized that. I'm recording it to the cloud for you.
Okay, great, thank you. All right, so I think we are going to get started here. So thank you all for coming in person, and thank you all for coming over Zoom. We're doing a sort of an experiment today where we're going to do our speaker hybrid over the over Zoom, and I've got it here displayed on the TV for you guys. And so we'll just get into this really quickly because we have a really exciting presentation about the San Andreas Fault by Dr. David Bowman. And so I'm going to hand it over to him now.
Thanks. It's really fun being able to present to all of you this way. It'd be more fun if we could all be in person, but through the magic of Zoom, I'm able to join you. I am a seismologist, spent many years in California at different universities. I was trained at USC, worked for many years at Cal State Fullerton. I've worked at the University of Paris, and I study how and why earthquakes happen. And I'm currently actually talking to you from Eastern Washington University, way up in the great Pacific Northwest, where I currently run the College of Science, Technology, Engineering, and Mathematics. But my heart is with the San Andreas and with earthquakes. I'm one of those weird people that loves earthquakes. And it's kind of fun talking to you all of there on Wrightwood about the San Andreas from my perch here in Washington, because you know, those of us, I've really learned that those of us that live outside of the state of California, when we talk about earthquakes and about earthquake hazards in the San Andreas, this is what everybody thinks. Let's see if I can make the slide advance. Yeah, this is what everybody thinks about earthquakes in California. It really, you know, the earth opens and, you know, monsters come out from the freeways. And I don't know, that may or may, thank you for laughing. I appreciate that. You know, we know the reality is not like that, in fact. There's faults all over California. Earthquakes are part of the fabric of what makes the state. If you had California with no earthquakes, that would be Kansas. You know, the beautiful mountains that you live in are there because of the faults and earthquakes that we have in the state. So it's a big part of the fabric of what makes California, California. And I should say, during the time of this talk, if you have questions, I know it's hard to manage with the technology. If folks have questions, you feel free to either raise your hand on Zoom and I'll try to answer them, or if you want to enter them into the chat, if you're joining remotely, I'm happy to try to answer questions through the chat that way as well. So the rest of the country sees California this way. And of course, we recognize that Southern California does have its faults, lots of them, thousands of faults throughout the region. The big one, the 800-pound gorilla that everybody talks about and everybody knows by name, is the San Andreas, which runs, it's that yellow line. Can you guys see my cursor okay? Yes, okay. So the San Andreas Fault runs right through here. It's the largest fault in the state. About 750 miles long, runs from the southernmost part of California up to Mendocino in Northern California. But there's a lot of other faults that happen throughout Southern California. Lots of myriad faults. Some you know the name of, perhaps the San Jacinto Fault, the Elsinore Fault, the Garlock Fault, all kinds of faults that produce large earthquakes throughout the region. San Andreas is just the biggest and most famous, and you care about it because it runs right through your town. Now, the San Andreas is itself part of one of the world's great system of tectonic plate boundaries. The Earth is broken up into pieces like stitching on a baseball. And with different plates that are constantly moving around with respect to each other and bumping into each other. And as those plates grind past each other in different orientations, they produce earthquakes and volcanoes and all of the topography that makes our planet. So in California, you are sitting on one of the world's great plate boundaries between the Pacific Ocean plate and North America. Up here in Washington, where I live, we sit near a different plate boundary. Up off the coast, western coast of the state of Washington, there's a small little ocean plate, tectonic plate, that's getting shoved underneath North America. And when that tiny little ocean plate melts as it's shoved deep into the Earth's interior, that melting of that plate is what causes the Cascade volcanoes like Mount Rainier. But we're going to focus in on California. And this is a different picture that shows California on its side, the western US on its side. And you can see right here, that blue line running along there is actually the San Andreas Fault. It divides the Pacific plate from the North American plate. And along the San Andreas Fault, the plates are grinding past each other as the Pacific plate moves off to the north. This has been going on for quite a long time. And since we are talking with the Historical Society, let's tell a little bit about the history of the fault. Of course, when a geologist talks about histories, we have lots of zeros after the numbers. The real history of the San Andreas Fault starts about 30 million years ago, when the plates and the planet did not look the way it does today. At that point, there was no Baja Peninsula here. Baja California was not split off. It was actually part of the mainland. And much of what we see along the coastline here does not look like what it does today. There were no Sierra Nevada mountains at that time. And so I'm going to click through a couple of different slides of cartoons of what the west of North America looked like at that time. So this is what that, I'm gonna go back. So this is the same thing. I tried to put it the same orientation here. The west coast held here horizontally. So the north is sort of up to the upper left-hand corner of your picture. And this is what it looks like in this cartoon of the coast of North America 30 million years ago. Here's roughly where the coastline was. This is where modern day Los Angeles would have sit in that old paleo geography. At that time, there was still an ocean off the coast of North America, but that ocean was a body of rock that we call now the Farallon Plate. The Farallon Plate is gone. It doesn't exist anymore. The remnants of that plate are what we see right up here. The modern day, what's called the Juan de Fuca Plate, is actually the remnants of the old Farallon Plate that's now almost entirely gone. And the reason it's gone is because through time, that Farallon Plate has been shoved underneath North America. That's what those little barbed lines on here indicate, that this ocean plate is being shoved underneath North America. And 30 million years ago, not only did we have the Farallon Plate, but there was another ocean plate here, the modern day Pacific Plate, that was separated from Farallon with here a mid-ocean ridge. So I'm going to go back to our map of the world. And the different plate boundaries that you get right here in Southern California, the San Andreas is where the plates are sliding past each other. Here along the west coast of Washington state is where one plate is getting shoved underneath another. But way out in the coast, and I'll move to this one to show you, these areas right here are where the ocean plate is actually getting pulled apart. A new ocean plate is being created and it's spreading that plate apart. So the ocean crust right here is brand new. It was just formed yesterday in geologic time. And so this is an example of a new plate that's being formed in the middle of the ocean, being shoved underneath North America here in modern day Washington and Oregon. 30 million years ago, that's what was happening off of the coast of North America. There was one of these areas where the ocean was being spread apart, making a new ocean plate right here while the old one was shoved under North America. If we fast forward in time to 20 million years ago, let's fast forward in time, there we go. That ocean plate started to get shoved under North America, and this boundary between North America and the ocean plates changed. Now you'll see that the Farallon Plate that we had previously, you can see what happened. That got rammed in and it got broken into two smaller plates, the Juan de Fuca Plate, which is what exists today off the coast of Washington, and the Cocos Plate, which actually still exists, but much further south down off the coast of Mexico. And in between these two areas was the ancestor of the San Andreas Fault, formed about 20 to 30 million years ago from the collision of that old Farallon plate. And through time, as that plate continued to get shoved underneath North America, the San Andreas got bigger and longer and longer. And it's really interesting what happened in this time. There's all kinds of pieces of the coastline here that was getting shaved off of the coast of North America and shoved up north as motion along that plate boundary. In fact, most of where I'm sitting in Washington and a lot of modern day Alaska has pieces of the ocean's crust that started out down in California. And were shoved northwards along what would eventually become the San Andreas Fault. This is called Baja, British Columbia, as the plate boundary here would take pieces of Baja, California, and shove them north to become parts of British Columbia and the Pacific Northwest. Kind of cool. So this is what the plate boundary looked like about 10 million years ago as the ancestral San Andreas Fault got longer and longer. And this portion of the San Andreas, you can still see today. It's called the San Gabriel Fault, and I'll show you an image of what it looks like today. It's still preserved in the San Gabriel Mountains. You can drive there. So this is what it looked like about 10 million years ago. About 5 million years ago, something really cool started to happen. The San Andreas Fault, or the ancestral San Andreas, the San Gabriel Fault, moved through here, and this area where the spreading center that was creating new Pacific plate and pushing the Cocos away got down to a weak zone here at the southern part of the coast of Mexico. It's something really interesting happening that we don't fully understand why, but this little junction where the three plates come together, the North American, the Pacific, and the Cocos, cut into the continent and started to break off a huge chunk of continental Mexico and shove this whole area northwards. And that creates what we have as the modern San Andreas plate boundary system. So today, that old Cocos plate has a couple different pieces. It's getting slowly devoured by North America. And it is breaking off Baja. Baja used to be part of the North American plate, but what's happened is as this has migrated, Baja has broken off of North America and is now part of the same Pacific plate that Los Angeles sits on. Which is actually interesting in its own right, because LA and Baja and most of coastal California are not actually part of North America. They are part of the Pacific plate. So if we jump back and look at the map right here of the modern continent, all of this, Baja California, San Diego, LA, Santa Barbara, Santa Cruz, all of these are not actually part of North America. Something that probably doesn't surprise a lot of people, but geologically it's true. They're part of the Pacific plate. Wrightwood sits exactly on top of that blue line, is the boundary between the Pacific and North America. And so when we look at the modern system, Baja right here is actually being shoved northward because of these tiny little ocean basins that are forming inside the Gulf of California. So as the Gulf of California, as time goes on, the Gulf of California is going to get bigger and bigger and bigger. Baja is going to be shoved further and further north and will move northwards along the San Andreas, and LA will continue to be pushed northwards along the San Andreas, and eventually, someday in the future, Los Angeles will be sitting up at the latitude of San Francisco. And San Francisco will be shoved out of California entirely, off into the Pacific Northwest. In the very distant future. How fast is this happening? Well, the San Andreas Fault moves about as fast as your thumbnail grows, which doesn't seem very fast. You can sit and watch your thumbnail, it's not going anywhere. But if you don't trim your thumbnail for a week or 2 weeks or a year or 150 years, your thumbnail gets pretty long. It actually goes pretty far. It's about 30 millimeters a year is the rate at which this system is moving to the northwest. In fact, we can see that reflected in the geography of the state. So here's a different look of California with the San Andreas highlighted here, right? And you can actually see a volcano down here in Southern California that you can actually drive to off of the 14 freeway and see this old volcano that's got the lava flows from that volcano are way up here in north central California on the other side of the San Andreas Fault. That lava flow used to be down here and has been displaced 315 kilometers over the millions of years since that volcano erupted. I think that's pretty cool. And you can match up different areas of rocks across the San Andreas to see how far they've moved over time. Now, if we zoom in and look at the fault itself, it's really neat to be able to see the landscape and read where that boundary is. I'm going to start up here in Central California in the Carrizo Plain, because I think this is amazing personally. If we look at that part of the San Andreas here in the Carrizo Plain, this is what the plate boundary looks like. It's not very remarkable. There's a low line of hills with a really sharp dividing line here that actually represents almost all of the motion between the Pacific and North America where they're sliding past each other. It really comes down to almost entirely one fault. That's incredible to me. But what's really cool is you can see the fault here where there's streams on the hills that cut across the fault, and the streams are actually displaced by the fault over repeated earthquakes. And this is an area where you can see this stream. It's actually called Wallace Creek. Wallace Creek comes down here, hits the fault, and it's been offset during multiple earthquakes on the San Andreas Fault. And you can see another branch of it right here that continues along. That also is an old branch of Wallace Creek that's been sheared off by motion across the fault. This is a really neat place to drive to. It's in the Carrizo Plain National Monument. There's a butterfly preserve there. But if you drive up through the Carrizo Plain National Monument, there's a little pull off towards Wallace Creek. And it's a very short hike, about a 5-minute walk from the parking lot up to these drainage areas. And you can actually stand with 1 foot on the Pacific and 1 foot on North America and really see clearly where the fault is. This is a different view of that from the road that goes towards Wallace Creek. And again, you can see I'm standing here in the Pacific Plate. That's the North American Plate. And all those low hills are there created by the San Andreas. It's totally unremarkable unless you know what you're looking at. From the air, it's really spectacular. If you look at it from the air, give you a chance to guess where the San Andreas is. It's this sharp line that runs right across here. So this is actually to the northwest. This is towards the southeast. And the San Andreas is that line that runs right through there. That's the fault, razor sharp. Here's Wallace Creek cutting across. You can see that an older version of Wallace Creek here and even hints of older ones over there. This is that little parking lot that I mentioned that you can go to and walk up to the fault and walk all along the fault back and forth here. Well worth a day trip sometime. But what's remarkable to me is that in this area, the fault is very, very straight. And so the motion is almost entirely taking up just on the San Andreas Fault. If I go back to that map that I showed you early on of Southern California's faults, we're standing right there on that picture. And you can see that there's really just one major fault that is taking almost all of the motion between North America and the Pacific. But down here in Southern California, things get messy real fast. There's a lot more faults that you see through this area. And if we go back to here, So here's the San Andreas, just one single fault on this nice straight section. But you'll see that the San Andreas does something here. It's got a big, gigantic bend in the fault right around the LA area. This big, gigantic bend in the fault is very special to geologists and earth scientists. It has its own name. It's very creatively called the Big Bend in the San Andreas Fault. You can Google it, it's real. But the Big Bend in the San Andreas Fault has a huge impact on that plate motion. And it causes all kinds of other faults to occur, and it lifts up the San Gabriel and the San Bernardino Mountains and all of the transverse ranges. So this is an image of a topo map taken by the space shuttle with topography draped over it, a Landsat image draped over it, and you can see there's the San Andreas Fault through the Great Bend. This is a snapshot of the Big Bend in the San Andreas. The part that we're looking, the straight part is up here on this. There's the San Andreas. You could see that knife edge cutting along the faults. This is the where Wrightwood is right there, and there's the San Gabriel Mountains. And unlike what we saw in the central San Andreas, here you get ginormous mountains that form. And the reason that that happens, and it makes all the reason those mountains are there are because all of these faults, those faults lift up the mountains. And the reason it's there is because of the Big Bend that causes compression across the fault. It's the Pacific plate to the south of us from Baja California is actually ramming into, it's rear-ending North America. And just like two cars, a car that rear ends on the freeway and the hood of the car crumples as that collision happens, that's what's happening. This is like a car crash with the hood of the car crumpling and creating those mountains and all of the faults that we see through Southern California. So all of this, everything that we see in Southern California gets its origin from that Big Bend in the San Andreas. If we look at this a little bit further, and I'm going to say, Morgan, tell me when I've got 5 or 10 minutes left, so I stop for you, because my clock is covered up by this.
I will do. Yes.
So I'm going to do is walk you through this really quickly here. So this is a map of active faults through the Western US, and we're going to zoom in and actually take a quick tour of the San Andreas. So let's fly into LA proper, and you'll notice that these are all active faults. There's two different colors. Those light orange faults are faults that have not had an earthquake within historic times, within the last 150 years or so, 200 years. The red are parts of faults that have had earthquakes within the recent past. So for instance, this portion of the San Andreas, and you're sitting right there right now, this portion of the San Andreas last broke in 1857, right? In the Great Fort Tejon earthquake of 1857. So that is the length of the historic break. It was a huge earthquake. It broke from Cajon Pass all the way up past where I showed you the photos before to the little town of Parkfield in Central California. Huge magnitude 8 earthquake. This was the 1992 Landers earthquake. This is the break from the 1999 Hector Mine earthquake, and so on and so forth. These all represent historic earthquakes in time. This was the Kern County earthquake in the 1950s. So as we zoom in, one of the things that's really interesting here, I'm going to point out because y'all drive through it often. This area right here is fascinating to geologists. This is an area where 3 different faults come together. This is the San Jacinto Fault, which itself is a large fault capable of producing a magnitude 7, 7.5 earthquake. And of course, this is the San Andreas that runs through here. And this is the Sierra Madre Rancho Cucamonga fault system. Itself is the main fault that's lifting up the San Gabriel Mountains and could also produce a magnitude 7.5 earthquake. All three of those faults come together at one big knot there in Cajon Pass. That you can see when you drive by on the 15 freeway. And one of the big questions that we as earthquake scientists have is, can you have an earthquake that starts on the San Andreas, ruptures through here, and then leaves the San Andreas, but jumps on to the Rancho Cucamonga Fault? Don't know. Could you have an earthquake that starts on the San Jacinto and jumps onto the San Andreas? Don't know. It's possible. We've never seen it happen, but that doesn't mean it can't. So it's a really interesting area. And that intersection of those three faults has a big impact on what you see in the topography. So let's zoom in. So we'll take a look at all these different faults and then zoom in here to that knot. It's what a colleague of mine, Lynn Sykes at Columbia University, calls a tectonic knot of all these faults tied together. You can see where they come together. The 15 freeway runs right through here before it comes over through the pass. Cal State San Bernardino is right over here, right on the fault. And as we zoom in closer, I love doing this when we used to live in LA and would drive up to Wrightwood, and you drive along the freeway here and you can look in the hillside and see the slope of the basin goes up real smoothly, and then there's a big cliff and then it goes up smoothly again. That cliff that you see there is the Cucamonga Fault running right through there. And you can actually see it very clearly in the hillside, and you can see that there's houses built up, and then there's a gap with nothing, and then houses again. That gap where there are no houses, that's where the fault hits the surface. So as we zoom in further, so here's where we come through the Cajon Pass, Devore right through here, and you'll see the different faults that run up through these canyons. Faults are weak zones in the Earth's crust. There's zones where the rock has been crushed a lot. It erodes away very easily. And so rivers like to follow fault zones. They're easy to erode away. And so Lytle Creek, when you see come through here, Lytle Creek and a lot of the other creeks that run through the area are actually following ancient fault systems. And this one in particular was the one of the old ancestral branches of the San Andreas from before 5 million years ago that I had mentioned before. This branch, the modern San Andreas that goes through Lone Pine Canyon, Swarthout Canyon here, and right underneath Wrightwood, is the youngest branch. It's only 5 million years old. So as we come through the intersection here with the 15 to 215 and drive along the 15 through here, you're actually have the San Andreas Fault off to your right as you're driving up along the pass there. And when you get to that big turn in the 15, you're going to actually drive right across the San Andreas, right through here. It's hard to see looking back towards the south, but when you get even with Lone Pine Canyon off on your left as you're driving north on the freeway, that's when you're crossing the San Andreas. And as you drive along it, you can actually look back and see where the fault is cutting through the hillsides here. So the fault comes right through here, and you could really see this spectacularly from the cutout along here, from the old Route 66. But as you look back, either on Route 66 or on the 15, you can see where the fault cuts through, and the side of the hill right here is all a really pretty blue color. That's an area that's called Blue Cut. And the reason it's blue is because the rocks have been metamorphosed. Their composition has been changed by motion along the fault, letting water get in there and change the composition of the rock. It's actually turned into a kind of clay by motion on the fault. Blue cut is actually on the San Andreas Fault. And I'm going to pause here for a second as well before we swoop along and continue flying along Swarthout Canyon and Lone Pine Canyon, because there's a lot that you can see in the topography of the ground that are clues to where the fault is. So there's a couple of different things I'll point out really quickly right here, and we'll start to fly over them a little bit. There's two big geographic features that you can see that are hints to where the fault is. One are these little lakes. You know this, sag ponds. Lost Lake is a sag pond. And what a sag pond is I mentioned earlier that when a fault grinds along through the crust, it makes a weak zone of crushed rock that's easy to erode. It also makes a zone where oftentimes the ground will sort of sag in, it'll dip in, make a small depression that fills up really easily with water. So sag, because the ground appears to be sagging, and pond, it fills with water. So Lost Lake is a sag pond formed in the San Andreas. They also tend to get a lot of ponds through here because oftentimes one side of the fault will be really high. You'll have mountains, and sometimes you'll have on both sides. And so you've got this weak zone here of crushed rock. And the crushed rock acts like a dam inside the earth. And so groundwater that soaks into the ground up here and seeps underground through aquifers, seeps downhill. It'll keep seeping downhill until it hits the fault right here, and the fault acts like a dam underwater that makes that water pond up and come to the surface along sag ponds through damming groundwater flow. So sag ponds are a great indicator of a fault like the San Andreas buried at depth. The other thing that you see right here are features like this, these low set of cliffs that are all one-sided. That is formed when you have a hillside that comes across and gets sheared off by the fault, leaving this low cliff along one side of them called a shutter ridge. And you'll see them all along Lone Pine Canyon as we fly up it. And next time you drive Lone Pine Canyon, I encourage you to go keep an eye out for them. So as we fly over, you can see one of those shutter ridges really clearly right here. The big depression, that's where Lost Lake was. If we weren't in such a dry climate, Lost Lake could be bigger. This whole depression is an area where you might see water at different climate zones. You'll also see how there's more greenery through here. That's because of this fault zone through here acts as a pond for water underground, and along the fault zone itself you'll often see a lot of much better greener living trees and more vegetation preserved because there's ample groundwater close to the surface because of the fault. Dead brown stuff over here, nice green in here because of the fault itself. So we're going to keep flying along the San Andreas here, up Swarthout Canyon Road and towards Lone Pine Canyon. Did I start? Let's keep flying. Okay, so we're going to stop. The program was not behaving with me there, sorry. So we'll let this start up again and get to where we were. But as we fly up the canyon here, keep an eye out on the left once we get to that part of the show again for the topography changing. There we go. We'll let it go now. So keep an eye on the left, and you can see these ridges that are caused by motion on the fault that are chopping off old hillsides and moving them along. And you can see this all the way along through here, right? When you drive, if you drive the Swarthout Canyon Road, you can see all these little, very, very low, hard to see hills just off to the west. Those are all the sections of the San Andreas where the San Andreas comes through. So here's the junction between Swarthout Canyon and Lone Pine Canyon Road. If you come in off the freeway, off the back way up through Lone Pine, you will drive with the San Andreas on your left-hand side at the base of the hills all the way through. Personally, when we drive to Wrightwood, My family and I, we always drive along Lone Pine Canyon because it's fun to drive along the San Andreas, and every minute we drive along there is another chance that we might be there when an earthquake happens. And like I said, I love earthquakes. That's cool to me. So as you drive along here, you can see on the west these low line of small, tiny little cliffs that actually represent the San Andreas Fault. You'll see all the a lot of the ranches are built there because it's easy to get groundwater when these were being established. You'll see orchards and everything, oftentimes natural, growing along where that San Andreas, because the water comes down off of the San Gabriel Mountains and ponds underground along the San Andreas. Keep driving along the Lone Pine Canyon into town, and you'll actually cross the fault a couple different times here in that big curve. This is where that old limestone quarry was. And when you get the old limestone quarry through here, just at that curve is where you cross the San Andreas. You come across through here, and when you take that last curve past where this is Circle Mountain, and I think this is called Helicopter Hill, is that right? Right through there, that's right where the San Andreas, where you make that curve to go into town. And when you make the curve on Lone Pine to get into this part of Wrightwood, flying into Wrightwood, you are driving along the San Andreas the whole way there. Lone Pine Canyon, as you enter Wrightwood proper, is actually right on top of the San Andreas Fault. So as we drive through here, there's San Andreas. When you get over to Sheep Creek, no, this is Heath Creek. When you get over to here, right when you go through where the wash is, the San Andreas is just off to your left. I'll go slow so everybody can look where their houses are. I know everybody wants to do that. This is the active part of the San Andreas. You can see where all of your houses are relative to San Andreas. And I have to say, you can look where your house is relative to the San Andreas, but frankly, this entire valley is riddled with fault systems. This is the fault that broke the last time in 1857. It's highly likely that that's where the next earthquake will occur on, but it could jump to a different one of these strands. There are strands of fault all the way through here. And it could be that an earthquake could go through any one of these sections. It wouldn't surprise me if that happened. As you continue in through Wrightwood, we'll of course make a stop where you're all sitting here at the Historical Society. The San Andreas Trace is just north up the hill. As you go out of town towards the west, you'll see the low ridge where the hill goes up over here. That is where the San Andreas is actually, there's two strands that are squeezing it together and popping this little ridge up. As you continue west along the freeway, the two, you'll keep seeing the San Andreas on your left, and you get up here towards Mountain High East. The San Andreas is actually right through here underneath the highway itself. There's also some strands that might run through here, and there's some debate. There's probably multiple strands that run right through where the base of Mountain High East is, but you can see it right there. So there's the fault going under the freeway. And as we continue towards Mountain High West and Big Pines, this is where the fault goes. And here the two goes now in that way towards Pasadena, and there's that branch towards the two other roads. We're going to follow N4 through here, Big Pines Highway. So as you stay on Big Pines Highway, you're going to continue to follow the San Andreas. And this is one of my favorite stretches of road anywhere. I'd love driving this stretch of Big Pine Highway. You cross the fault multiple times. So you cross the fault through here, and as you go Big Pines Highway towards Jackson Lake, you'll get to these little curves just after you leave the two, where you see all kinds of bluish green and gray areas that are sort of shoved up a little bit on either side of the road. That's actually crushed rock from the fault. It's something that's called fault gouge. So you take the fault, And as you're continuously grinding past each other, you're fracturing the rock inside, and it's making this thing called fault gouge, which is all really highly fractured rock. Sometimes it's called rock flour. The rock through here tends to be a lot of schist, as you know, living in Wrightwood, but also some granites in the area. And it's all been completely pulverized by motion along the fault. And when you drive through some of these picnic areas on here, you actually can park and actually stand on the gouge from the core of the San Andreas Fault. As you, this is a nice little picnic area right here. When you drive along the fault through here, you'll see it goes into a deep valley. That valley is actually the valley of the San Andreas Fault. And when you keep driving along this part of the Big Pines Highway, you get to the area with those big switchbacks that go back and forth. Again, one of my favorite things to do, and when I lived in California, I used to love taking field trips through here, because you drive along the pulverized fault gouge of the San Andreas, and then as you drive away and go towards the east here on one of these switchbacks, you can look at the rock off to your side and see the amount of fractures in the rock be getting less and less and less as you move away from the active trace of the fault. And then you go around the switchback and come back over here, and you go back into the highly fractured parts of the fault through here as you get back to the main modern course of the San Andreas. Very cool thing to do. As you drive along through here, you get to another one of the most picturesque parts of the San Andreas, Jackson Lake. Jackson Lake is another sag pond on the San Andreas. It runs right through here. And actually, it's neat when you go out into Jackson Lake, you could see lines of reeds growing through up through the bottom of the lake. Those are actually following different strands of the fault as it cuts through this area that are submerged by the lake. As you keep going along Big Pines Highway towards Palmdale, we'll fly there in a sec. You basically, the Big Pines Highway is on top of the fault almost the entire time. That as you drive down through Mile High through here, this is, oh my gosh, I forgot, Caldwell Lake, I think this is called. This is another one of those sag ponds, but highly modified by people. And as you keep driving along that, you get to Valyermo, which is again right on top of the fault. And you can see where the stream has come through here and it cuts, and it's all very naturally green. Obviously, it's also modified for agriculture, but it you get a lot of green through here and good land because of ponding against the San Andreas Fault right through there. So there's Valyermo. You keep coming around and you come back to this area that we'll take a look at. So this is at the corner of Fort Tejon and Pallet Creek Road. This is Pallet Creek. And this area is probably one of the most famous places that nobody's ever heard of. It's very famous for geologists because this area in Pallet Creek is an area that there's ponding of water and standing water that sits at Pallet Creek. And there's been a swamp there for thousands and thousands of years. And the reason that the swamp is important is because when you have a swamp, you get standing water and the reeds and all the biological stuff that's there in that swamp area dies and it sinks to the bottom and it makes a bog, it makes peat. And so this area is actually a bit of a peat bog. And it has been constantly having sediment washed in from off of the San Gabriel Mountains and burying the peat bog periodically. So you have a very, very thick layer of sediment. And it's sliced by the San Andreas. And you can go here into Pallet Creek and see, dig a trench across the peat bog there and see the different layers of the peat bogs through time as they've been deposited through time, and see where the San Andreas Fault has sliced it. And the reason the peat bog is so important is because peat is full of carbon, which you can radiocarbon date. And it was in this area along the San Andreas at Pallet Creek where people first were able to using radiocarbon dating to get the past history of earthquakes on the San Andreas Fault. And all this entirely new discipline was formed called paleoseismology, ancient seismology earthquake study, that is based on using this technique of dating ancient carbon layers fundamentally to figure out the past history of earthquakes. We'll see that in a second. So Pala Creek is super important part of the story for the San Andreas. But of course, the reason we care about this is because the San Andreas causes earthquakes. So what can we expect when we have an earthquake? We didn't have seismometers in 1857 for the last big earthquake on the San Andreas. And the reason we care about earthquakes on the San Andreas is because the San Andreas, first of all, it's huge. It's capable of having magnitude 8 earthquakes with one of the world's great cities sitting right here off to the side. And because of the geography here, LA and all of LA, Orange County, San Diego get all of their lifelines from the other side of the fault. Most of our power comes across the fault. The water crosses the fault. Oil pipelines cross the fault. Transportation, oops, we got the earthquake happening. Everything that happens here, I'm gonna go back so the earthquake doesn't distract us. Everything that happens here on the fault right here crosses, or that feeds LA, crosses that fault. So we want to understand what potential earthquakes are. So this is a simulation of what a potential earthquake might be on the San Andreas. The colors are the earthquake waves that are rippling out. This is an earthquake that is simulated to start down in the Salton Sea, where the San Andreas begins, and to rupture northwards along the San Andreas to right about here. It's the size of an earthquake and a stretch of fault that we believe, through doing those trenching that I talked about earlier, is very ready for an earthquake. So this shows the earthquake waves rippling through. You'll notice that this earthquake's been going for 49, 50 seconds, and it hasn't even hit Wrightwood yet. An earthquake this big, magnitude 8 something here, now you can hear the shaking here in Wrightwood as the earthquake has arrived. An earthquake of that size will be about a magnitude 8 to 8.1, and it will be devastating to much of the region. I'm going to see if I can mute my sound on here. That would be devastating to the region. You can see all the shaking that's happening. One of the reasons that we're concerned about an earthquake on the San Andreas is because the LA basin right here is a big zone that's filled with sediment. And when an earthquake happens, earthquake waves get trapped in that sediment and make it shake like a bowl of jello. So when an earthquake happens on the San Andreas here, the shaking will continue in LA and Orange counties long after the earthquake itself is over. And also in other valleys like Oxnard Valley and some of these areas, and the San Fernando Valley, the shaking gets trapped and lasts for a long time. We're over 2 minutes into this earthquake and we've still got shaking going on. That's one of the reasons that people are worried about the so-called big one on the San Andreas. But this is the shaking. The earthquake itself, the breaking of the ground along the fault, is long done by now. If we rewind along this, the earthquake started, whoop, right there, and it ruptured northwards. The actual ground breaking took, boom, a minute to get to Wrightwood. And then it comes up through here, through Lancaster, to roughly Palmdale, right there. This is a minute and 40 seconds. The ground breaking itself along the fault has ended, but the shaking continues. And I should say, this is what's called the shakeout scenario. So the third Thursday of every October is when you have the Great California Shakeout, statewide earthquake drill. This was the first one that we did in 2008. And all of the earthquake drills since then are based on this concept of the shakeout. And this was a model that was originally done to really understand what the impact of this earthquake would be on California and on the infrastructure. It was really important because we learned about, from an earthquake of that size, where the power vulnerabilities are, where the water line vulnerabilities are, how much it would take to get the cities in the region back up. Really important for that. This particular part of the simulation was run by my friend Rob Graves, who now is running the USGS in Pasadena. And there are many, many other different versions of these kinds of scenarios for different big earthquakes. It's different. What happens if it starts down here and runs that way? What happens if it starts here in that tectonic knot and runs in both directions? All of them have different impacts and different shaking that can be produced. If we go forward and look at the Cajon Pass itself, so this is a different view of that same model of the earthquake. So we'll start the rupture going. You'll see on the left-hand side here is the earthquake spreading out. And in this case, the colors between blue to red are showing the severity of shaking, strong shaking. And you're going to be able to see here the rupture core come towards us along the San Andreas. Now I'm going to pause for a second because the shaking is going to reach us before the actual motion of the ground happens. The shaking from the earthquake actually moves faster than the cracking of the ground. And this topography and the shaking is actually significantly exaggerated, 1,000 times higher. So it's not going to shake this much. I just want to warn you when you see what the ground distortion does. And it's also 1,000 times exaggerated so you can see. So when the earthquake gets here, the right-hand side of the fault is moving towards you. That's the Pacific plate. And you're going to see these mountains come shooting towards you from displacement. It's not going to be that much. It's actually only going to be a few meters, which is still a lot, but not like a half a mile the way it's going to look on here. So let's watch, whoops. Let's watch the earthquake comes towards us again. Okay, so you'll be able to see ominously the colors marching towards us on the San Andreas Fault. When I used to teach this in class, I would play the Imperial March from Star Wars in the background as the evil force is coming towards you. So here we see the shaking coming towards us. At this point, you in Wrightwood would have no idea that an earthquake's happened, but it's already 30 seconds into it. Okay, and only right now, when the blue gets towards us, is when you feel the first jiggling, and everybody goes, "Oh my God, is that an earthquake?" So that's the beginning of being able to actually feel shaking from the earthquake, the first waves that are hitting us. But the fault has not actually started to move yet. And you'll see as this keeps going, we'll be able to watch. You see the ground jiggling from there, from the distortion of the Earth's surface from the earthquake wave moving. Now you can start to see this red front is where the actual ground motion is. And you can see the red line of the fault rippling. That's the ground actually sliding, the two sides of the fault sliding past each other. Here's the rupture front going to come past us and boom, shove all of these to the right from the distortion on the fault. Again, 1,000 times exaggerated so you can see it, but it's still pretty dramatic. The 15 there will be cut off by the fault. There are power lines that run through there that we have to build to withstand the movement of the fault. Water that goes through there, oil that goes through there. This is one of the major lifelines for the LA basin, and obviously pretty significant in Wrightwood as well. So at this point, for us here in Wrightwood, the earthquake's basically over. If you look at the ground, you still see it sort of rolling a little bit. You'll still have rolling motions, but for our purposes, the earthquake for us is done, even though there's still 20 more seconds of earthquake rupture towards the north. This is a really significant event. And again, lessons learned. I just want to highlight this one because it's such shocking to a lot of people. Lessons learned from this, because the water conveyance to get into Southern California goes across the San Andreas. Everything goes across the San Andreas. And concrete and iron pipes are brittle. They're going to break in many places. This scenario projected when it was done in 2008 that it could take as long as 6 months before you get water back in the taps. And if there's one thing we've learned from the pandemic is that some of these things can take even longer as you get to equipment shortages. Our economy is built for just-in-time delivery of goods. Well, if all of Southern California all of a sudden needs new water pipes, it's very hard to meet just-in-time delivery. That's why we say 6 months here. And the cost for water and sewer alone will be $1 billion in 2008 dollars. So that sounds frightening, but the good news is we know about it. And so we can plan for it, right? And the reason we do these scenarios is so we can understand where the hazards are, where the risks are, and to plan to mitigate for them in the future so that we're ready when it does happen. And I will say that no place is as ready for earthquakes as California. And I include much of Japan in that. No place is as prepared for earthquakes as California. Doesn't mean we can't be better prepared. There's still things that we can do and need to work on. And it's studies like this that help us understand that. I'm going to go quickly through some of this just because we're running short on time here. One of the things everybody wants to know is how often do they produce earthquakes? I just want to show this, sorry for a graph, but I'm a seismologist. And this to me is one of the coolest things in all of science because nobody knows why it happens. This is something that's called the Gutenberg-Richter relation, Richter as in the Richter scale. And what it shows is on this axis, number of earthquakes, cumulative number of earthquakes, and it's log scale. So every tick mark is a factor of 10 more. And across here on the bottom are magnitude of earthquakes. And this is for data. This is real data for all of California. And you can see that there's this linear relationship, right? Every time you go one magnitude higher, you get about 10 times as many earthquakes. And that relationship holds everywhere in the world. If you want to know the number of 6 versus 5s, you've always, everywhere in the world, along a plate boundary like California, you've always got 5 times more 10s than 6s, 5 times more 4s than 5s, 5 times more 3s than 4s. We have no idea why that is. It's one of the great unsolved mysteries of science, but it holds everywhere. The only difference is the overall level of activity. The same relationship holds in New York State. The difference is the rate of 5s is just a lot lower. You could do this for the whole planet and ask how earthquakes occur. It follows this same relation. Big magnitude 9 earthquakes happen once about every 20 years somewhere in the world. Magnitude 8s, about every year or so, there's a magnitude 8. Every 2.5 weeks, somewhere in the world, there's a 7. Every 3 days, somewhere in the world, there's a 6, so on and so forth. Southern California, you could do the same thing. In Southern California, a magnitude earthquake happens about every 133 years, just based on that statistical relationship. Magnitude 7s about every 16 years, so on and so forth, down to like magnitude 2s. Every 4 hours, there's a magnitude 2 earthquake somewhere in Southern California. But this is the one I want to highlight. That's the big one, right? That's a big San Andreas type earthquake. Just on this relationship, we know it should happen about every 133 years. And what's really cool is that geologists get the same thing. Paleoseismology that I mentioned earlier, this is an example of that, where there's a backhoe digging a trench across the fault, and you get a bunch of, this is a great job for graduate students, shove them into a hole in the ground and make them draw a picture of what the side of the wall looks like. And each one of these colors through here represents a layer of dirt, the ground surface at some point in the past, a peat layer. And all of these are the cracks from an earthquake that's happened. And so by digging along this fault, you could see this layer was broken by that earthquake. So it's older than that earthquake. This layer was broken by the earthquake. So it's older than the earthquake. If we come over here, you can follow this crack, goes up to here, it breaks the blue layer, but not the green layer. So if we can date this layer and date that layer, we know that the earthquake happened somewhere between there. And that's how we date how old past earthquakes on the fault were. And what's astonishing is that if you date the central portion of the San Andreas, where you all are, it has earthquakes by doing this about every 130 years. Exactly what you predict by just looking at the statistics of modern earthquakes. That's cool. That's really, really neat that that works. By taking all this data together, we can then make an estimate for all the faults that we can find, we can make an estimate of the probability of earthquakes happening throughout California. So this is California Hazard Map, the most recent version, that shows the likelihood of having ground motion or probability of an earthquake everywhere in Southern California over the next 30 years. So there's a roughly 60% chance of an earthquake on the San Andreas right along over here in the next 60 years. If we just do simple math, 1857 was the last big one. It has earthquakes about every 133 years. 1857 plus 133 is 1990, roughly. That's when the next big one on the San Andreas should happen. Well, of course, 1990 is long gone by. That's why we talk about this portion of the fault being overdue from an earthquake. And that's why we worry about that for the big one. And if I end it right here, this shows the major California faults, and you could talk about how likely it is relative to the long term to break. So when people talk about the San Andreas being overdue, this is what they mean. This area is more than 1 times longer than the earthquake fault has broken. It's ready for an earthquake. This part down here in Orange County, the Whittier Fault, is also overdue. San Jacinto is overdue. That's why we worry about those as being the threats for the next earthquake. So we're at 2 o'clock, so I'm gonna stop there and take any questions that you might have.
Okay, hold on. We have a question here. Go ahead.
Yeah, how much does it matter the distance you are at from the fault? Like we're really close to the fault, so does that mean we're more?
I will put one last thing on then. What to do, I'm sure that you all know this, but whenever we talk about earthquakes, I want to point out that what you should do in an earthquake is what we call drop, cover, and hold on. Get under a table, hold on to the table, and protect your head from debris falling around inside the house. Even in a big earthquake like the San Andreas, like the big one in San Andreas, and even in Wrightwood, when you're built right on top of the fault, the most hazardous thing you have from the earthquake is not the building falling down. Most of our construction, I mean, there will be buildings that will be troubled, but that's not what the greatest hazard in an earthquake is. The greatest hazard is that TV, right? It's the lights overhead. It's things getting flung around inside the building. And that's why we drop to the ground, cover, and hold on. That's absolutely the most important thing to do in an earthquake. And is it okay if I take 30 seconds to show a video? So I'm gonna put on an example of a video to illustrate why this is. So this is some work that are done by engineers who take gigantic shake tables and build buildings on them and shake them to see how they'll stand up to earthquake. So this is a gigantic table that shakes back and forth to simulate an earthquake. And they're going to put into this table the exact same shaking that happened in the 1994 Northridge earthquake at its worst shaking point. And they built a modern wood frame building on top of it and then shook it to see what happens. And I'm going to show you some videos from inside the this building built on top of that shake table, so you could see what happens in the earthquake. All right, as you can see, first and foremost, the house is just fine, but it's stuff getting flung around in the earthquake that's so dangerous. And I want to point out that in these, there's a couple different things to look for. This bedroom that they built had nothing secured to the walls, right? No earthquake straps, nothing is secured to the walls. So I'm going to go back and show again. Nothing secured to the walls. This one has things secured to the walls with a strap holding the TV on, a strap holding that to the wall. And you can see here, TV's getting flung around. In here, things are safe. Look down where your car is down there. They've got a water heater, a pair of water heaters built here. There's a water heater strapped to the wall, and there's a water heater without straps. And you watch in the earthquake, the unstrapped water heater tips over. The strapped one stays just fine. So this is, again, just to emphasize, the greatest hazard in an earthquake are things like not strapping your water heater in properly. It's TVs that are not strapped in place and get flung across the room. So that's why when you have an earthquake, the most important things are, first of all, do prevention beforehand. But then when the earthquake does happen, do like these people are doing and drop to the ground, hold on, and protect your head.
So just to
Any questions?
just to go back to her question. So what is the relationship between
Oh, hold on.
shaking and distance? And I would add to that distance of like distance from the fault, but then also depth of the earthquake, because I know that matters too.
Sorry, Morgan, I had it muted so that it wouldn't play any more silly music, and I didn't hear what you were saying.
Oh, I was to repeat the question and to go back to the previous question. What's the relationship between shaking and the distance you are from the fault, and then also the depth of the earthquake? I'll add that because I know that matters too.
Gotcha. Sorry, I sorry I missed that question. I have myself muted so you wouldn't hear the silly music on some of these videos or the sound on my computer. So I missed the questions. I apologize. So relationship between distance and the shaking. Great question. Obviously, the further you are from the earthquake, the shaking is going to be different. But what's even more important that people don't understand is the kind of shaking you get changes. When you're near an earthquake, you get a lot of really sharp jolting motion. And the further away you get from the earthquake, a lot of that sharp jolty motion goes away, it gets filtered, and you get more low frequency motion. And so when you're far from an earthquake, you'll feel a lot more sort of back and forth like this, rather than the sharp jolty stuff. And that has a big impact on the damage that'll happen to buildings and what you experience. And the reason why is that the earth acts like a filter. When you send the shaking from the earthquake through the earth, it tends to filter out the really high frequency shaking. It's kind of like when you go to a stoplight and you hear somebody in the car next to you with their music turned way up, but their windows are closed, right? And you pull up next to the car and all you hear is a deep bass, right? And if they put their window down, all of a sudden you realize they're playing Britney Spears at right? Really high frequency. But you don't hear that when their windows are up because the car acts like a filter that filters out the high frequency stuff. And all you hear is the boom, 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 the bass. The earth does that to earthquake waves because earthquake waves are basically sound waves moving through the earth. And so when you're near an earthquake, you get all that high frequency stuff. It hasn't been filtered out yet. And that's high frequency shaking is what's more hazardous to smaller buildings where you get that real sharp shaking if you're very, very close to it. The farther away you are, you filter out the high frequency waves, but you still preserve the low frequency, slow back and forth kind of waves. That's less concerning for small buildings, but actually more concerning for big buildings. And so one of the reasons that people are concerned about a big earthquake on the San Andreas is because those a big earthquake on the San Andreas will have greater hazard to high rises in downtown LA, for instance, than an earthquake that might happen right underneath them because of the way that those low frequency waves tend to dominate. And also an earthquake like the San Andreas is a really, really big, long fault. So it tends to produce more shaking in those low frequency bass type sound than it does in the high frequency waves. So the situation for you in Wrightwood is actually pretty good, despite being right on top of the fault, which means you're going to be nearer to the fault with stronger shaking. But because the San Andreas is a really big fault, it puts more of its energy into shaking into the low frequency waves than a smaller fault does. And so there's all kinds of those different variables that fit into it. And of course, a shallow earthquake is always more hazardous for people because the fault is breaking at the surface. Now, in California, all faults are shallow faults effectively. When I say shallow and deep, an earthquake that's at 7 kilometers depth, that's a shallow earthquake still. And a magnitude 6 earthquake, a 6.5 or bigger, that's at a depth of 7 kilometers, it will break the surface most likely. But once you get below about a magnitude 5, then they're not likely to break the surface anymore. Okay, so in California, all of those earthquakes are what we call shallow earthquakes. Where I live in California, it's different. Our faults go very, very deep inside the earth. We could have earthquakes in Washington that are 200 kilometers deep inside the earth. Those are not likely to cause as much damage because they're very, very deep and you don't get as much shaking up where we are. Whereas in California, you basically don't get any big earthquakes deeper than about 15 miles or so.
So we've got two more questions. I've got one here on the Zoom first that we're gonna do, and then I'll get to you. Sorry, they just submitted theirs like 5 minutes ago. Please describe the relationships between the San Andreas and the faults that form the Sierra Nevadas and the Great Basin in Nevada.
Great question. So really interesting question. So I'm going to pull up this image again. So the Sierra Nevada here, and let's see, do I have a better, I don't really have a good one handy for this in this slide deck, but right through here where the San Andreas is, the San Andreas through here is actually right now, let me use this one for a second. The San Andreas is right now in the process of changing and evolving again. This fault does not like this big bend. It would rather go straight across. And so this area where see all these faults right here, where I told you earlier, the Joshua Tree earthquake and the Hector Mine earthquake and the Landers earthquake, where they all happened. This is an area called the Eastern California Shear Zone. There's lots of faults that are just like San Andreas, but it's as if you were to go from the Salton Sea here at the beginning, and instead of making the bend, keep on going straight. That's what the San Andreas wants to do. And so a lot of geologists believe that this area is the future San Andreas that's in the process of forming over the next several million years. So as this portion of the Eastern California Shear Zone runs through here, it actually connects across this area to Owens Valley. And Owens Valley, this big fault right here is the Owens Valley Fault. It is a fault that's actually sliding past each other as well as popping up the Sierra Nevada mountains. So the Sierra Nevada mountains themselves are made up of the bottom, the deepest parts of an ancient volcano system that used to exist along the coastline of California back 20 million years ago when I showed you the evolution of the system of California. It is being brought to the surface now along this fault along the base of the Owens Valley, lifting up the Sierra Nevada while also sliding along. And eventually, a lot of people believe through time, this is going to cut right across and become the new San Andreas, and this part of the fault will go dead. And we will all here be part of the Pacific Plate rather than North America. Now, the basin and range here through Nevada is something a little bit different altogether. We're not exactly sure why the basin and range is there. When you go to Death Valley Panamint Valley, Death Valley, and eastwards all the way to Salt Lake City, you get this area that's called the Basin and Range, because you have deep basins and tall mountain ranges. Again, not very clever naming, but it works. And what's happening there is the Western North America is being stretched apart. And there's a couple different reasons that that might be happening. But basically what we think is fundamentally going on is there's hot mantle underneath the Earth's crust there that's heating up the Earth's crust and stretching it apart. And as the Pacific, as the San Andreas is moving and dragging California to the northwest, it's sort of sucking that eastern area, the Basin and Range, pulling it towards the Pacific a little bit. There might be other interesting things that are going on. Some people have postulated that if I go back to this earlier slide where I showed you the old history, some people have postulated that the old Farallon plate here that's going down is still there at depth, and as it's sinking down into the earth, it's making a hot area underneath it that's welling magma up, dragging the Nevada basin apart. There's all kinds of different ideas like that. We don't really know for sure, but fundamentally what they all come down to is really hot mantle underneath the crust that's allowing this to stretch and making this series of faults that are stretching the Earth's crust apart. Different system, but similar.
So we have one more question. Go ahead.
Okay, my question is probability that the San Andreas Fault will Salton Sea. I believe you said it'd take 30 seconds before it reached Wrightwood. So I know you're putting seismic instruments in the ground will forewarn people. Why wouldn't we be smart enough to do warning systems like they do for tsunamis? I mean, that's plenty of time for people to say, get shelter.
You're gonna love that question.
Yeah, okay, so that you're asking about earthquake early warning fundamentally, right? And the answer is yes, we are doing that right now. There is an earthquake early warning system that's being installed throughout California. It's being installed up here in Washington as well, to basically be able to give people a warning. Now, there's a few caveats. And I should say, this kind of earthquake early warning system already exists in Japan, and it has a prototype version in Mexico as well. It works easier for them though. And the reason why is I'm going to go up to this big map. It's hard to see on this scale, but here's Japan. And you can't really see on the scale, but the fault that causes the earthquakes, the big earthquakes in Japan, is pretty far offshore actually. And so you can actually sense the motion. If you've got seismometers buried on the seafloor, you can actually sense with 30 or 40 seconds before the earthquake shaking gets to the main island. Same thing here in Mexico. Mexico City is actually quite far inland, but it sits on an ancient dry lake, which amplifies shaking and jiggles a lot in an earthquake. So an earthquake that's 100 kilometers away or more on the coastline of Mexico can devastate Mexico City because the old ancient lake basin amplifies the shaking. So Mexico has put seismometers here. So if they sense an earthquake on the coast, they can warn Mexico City, stop the trains, roll up the doors in the fire stations, all those sorts of things. But they benefit by their geography. They're far from the faults that make the earthquakes. For us, the earthquakes are right underfoot. Now, that's not, a big earthquake on the San Andreas can help us if it starts down here. You're right, we could put a bunch of seismometers right there and get 30 seconds warning before we get here. But like I said, we don't know that the next earthquake will start there. It might start right here. It might start over here. We don't know where the next one is going to start. It might not even, the next big earthquake might not even be on the San Andreas. You know, in my lifetime, in all of our lifetimes, there's not been a big earthquake on the San Andreas in Southern California. They've all been on these little dinky faults off to the side, right? So the problem becomes having enough seismometers to give you enough of an early warning. But you can do it. and we are doing it right now. It's a prototype system. And the challenges are, first of all, you have to have a lot of seismometers to do it. And so that means investing money. You have to have really fast computers, because you don't want to just say, oh, there's shaking, it must be an earthquake, because maybe it's a car driving by, right? So you have to be able to sense lots of different shaking at lots of different seismometers, and to be able to have your system smart enough to say, that's not a really big train, that's an earthquake. That requires computer power to diagnose what's actually happening, okay? So you've added seconds onto that right off the bat, maybe 10 seconds. And then you have to beam that information to your centralized warning system, and then get the information out to everybody. That's maybe another second. So you may only have 11 seconds that you could shave off right off the top and say, you're not going to get any warning from that because you're too close to the earthquake. And the problem is, for most of the LA basin, that's where the actual earthquakes are happening, right underfoot. You don't get enough time to actually get enough warning. But on San Andreas, you can. And I will tell you that I've experienced this in real time. Before we moved away from California, when I was a faculty member at Cal State Fullerton, right before we moved, there was a magnitude 5-something-ish earthquake in La Habra, right near where my house was. And during the time that that earthquake happened, and during the aftershocks, we were out looking at the fault breaks, looking for fault breaks throughout the area, doing initial surveys. And we were listening to the radio, and in real time, I'd hear my friends in Pasadena at the USGS offices in Pasadena in the middle of press conferences saying, well, you know, we're talking about what's going on. And I would feel an earthquake, and I would text, you know, Lucy or Sue, some of the other the seismologists in Pasadena, say, we just had an aftershock, and you'd feel a few seconds, and they'd say, oh, we just got a text about an aftershock, and boom, there it is. And it was really cool to have this sort of multimedia earthquake where we were out in the field and could actually communicate. It was really fun at that time because we were doing it over Facebook, and we were getting Facebook early warning systems because we in Orange County would say, oh, just had an aftershock, and then a few seconds later, oh, yep, there it is in Pasadena. So we're actively doing this right now. The system is there, it's a prototype. One of the big challenges is false alarms. You got to make sure that your system doesn't give all kinds of false alarms, because that can actually cause more harm than what it's worth fundamentally. We're working on it. The technology is fantastic. It's really impressive. There's a great group at the USGS and other places that are working on these things now. And I hope to see a reasonable warning system for big earthquakes on the San Andreas within the next few years. And in fact, the current early warning system, you can download the prototype off of, you know, for your iPhone, and actually download it and get the prototype warnings now.
Yeah, we just have one more question really quick.
Yeah.
Sure.
Is there any way you can predict what the offset would be on the San Andreas Fault at Wrightwood, like elevation change expected with the magnitude, let's say 8 or 9?
Yes, absolutely. And that's a big part of what geologists do. So, and that's really important information. We don't know how reproducible, I mean, how often it does exactly the same thing, but usually you can predict fairly well what the offset will be. And that's something that geologists do anywhere that you have active faulting. It's one of these things that when you're in an area around a fault in the state of California, there's what's called the special studies zone. That state law says that if you are building something in the area of a fault, you have to excavate where that fault is and get all of that information. The reason it's important is that you can then engineer your structures to withstand that. Now, not necessarily houses. If you're talking about a building, you're just going to keep it away from the fault. But some things like a power line or a water line have to cross the fault at some point. And so you want to build them to be able to withstand that offset that you're talking about. We absolutely do that to this day. And in a lot of the areas where, say, the aqueduct crossed the fault, you'll see that the aqueduct gets really, really wide. And you say, why would you build an aqueduct in a desert that's so wide? Well, the reason why is it's where the fault is crossing. And they're building the aqueduct wide enough that if the fault breaks, the aqueduct will still be through going for water to flow, right? Because normally in the desert, you want the aqueduct to be really narrow to prevent evaporation. They build it wide to protect for earthquakes. Another great example is actually not from California. It's from a big earthquake that happened in the early 2000s in Alaska, the Denali earthquake. The Denali earthquake was a fault just like the San Andreas where they slide past each other. And in Alaska, they have to worry about the Alaska pipeline, right? The oil pipeline. So the oil pipeline has to cross the Denali Fault. It's a big fault just like the San Andreas. And they know that they have to cross it. So how do you build a big oil pipeline so that it won't get cut in half in the earthquake? Well, what they did is geologists went and did exactly what you asked about. They looked at past earthquakes. They saw what the average displacement in an earthquake had been in the past. And then in that area where the Alaska pipeline crosses the Denali Fault, they built metal skids 1.5 times the size of the expected displacement. And the oil pipeline actually sits on metal skids so that above ground, so that if the fault breaks, the oil pipeline would just sit on these skids and the skids would slide underneath it, preventing the pipeline from breaking. And when it had that earthquake in 2001, it's exactly what happened. The fault break was exactly what the geology predicted. The metal plates, the pipeline slid across it exactly the way we predicted it would, and the pipeline was completely intact. No oil spill happened, even though that pipeline crossed the Denali Fault. That's what we're doing in California for all these critical infrastructure, is to understand the geology, understand what the fault will do, and build the infrastructure able to withstand it. That's why we do all those big studies. Great question.
Okay, well, it seems like, do we have any more questions? I think that's one more.
A quick one.
Yeah, we've got time.
Okay, true or false? Because there's a lot of granite in Wrightwood, we're less likely to be severely impacted by earthquake.
Ooh, good question. Yes and no. It's true and false. So here's what. So the granite transmits seismic waves really easily. So you'll get the full shaking from the earthquake. The reason I think what you're getting at is that in like Los Angeles, for instance, or in the valley areas like Valiermo, where that sediment basin is, it's the soft sediment that actually amplifies the ground shaking. It makes the shaking worse than it normally would be. So the granite that you're getting doesn't make the earthquake feel worse. It makes the earthquake be exactly what it is. And so it's actually the opposite, that in areas like the LA basin, where there's lots of soft sediment, the ground motion is actually worse than it would be if it was on granite. Does that make sense?
So it's like if I'm interpreting what you're saying correctly, granite is the baseline of what the shaking would be. And then if you are in sand, then it's worse.
Exactly right.
It's the exact reverse of what you were asking, is that granite doesn't make it better, it makes it exactly what it is. And then the sand in the LA basin amplifies it and makes it worse.
Exactly right.
One more question.
Okay.
What was the offset in Landers when they had that earthquake out there?
It was, let's see, what was, I can't remember the exact amount, but it was about 1 to 2 meters. Is Chris online? Nope, she's not. So my cheat sheet isn't here, my geologist wife. But my memory in Landers, it was about 1 to 2 meters. Whereas the offset you might get in Landers will be about twice that easily.
Yeah.
Okay. So thank you so much. It was a really, really fascinating talk. I think everyone else agreed. I forgot to tell you that it was 2:00 to tell you to wrap up. It was that interesting. So Anyone who's on the Zoom or in the meeting, if you were just here for the presentation, you can go ahead and take your leave. We're going to do a really quick general meeting for the Historical Society right now. So we'll have about a couple minute break to let everybody sort of disperse as they would like.
Does this information you just imparted to us show up anywhere in a video that, like on one of the channels that on the regular television we could dial up and get to see? Have you really opened a lot of doors that people need to know?
So there are a number of resources that I would recommend. The best place to go is on the web to earthquakecountry.info, right? Earthquakecountry, all one word, .info. That has almost all of this accumulated. It's a really great authoritative source maintained by the Southern California Earthquake Center and the USGS that really has good info on that. But I know you got to be careful because there's a lot of misinformation out there. But I really strongly encourage you, earthquakecountry.info, fantastic resource. Almost all of this is there in one form or another because it's people like me that made that website. So I'd really strongly encourage you to go there.
Earthquake.info.
Earthquake Country. Yeah, and what I'll do is I can have David email me a list of sources and resources and things like that, and then I'll send that out in an email blast to the entire membership for anyone who either missed, the talk and everything like that. And then this was also recorded. So this will be part of the Historical Society's archives now. And so anytime you want to view it, you can either put in a request to me or you can come into our archive and see it.
Okay.
And I'll put this up here. I had it at the very end, but here's a bunch of different great resources for you to get online.
Yeah.
Will those all show up on the program that she's going to copy?
Yeah, I'll have them send all those to me, and then I can have them all dispersed out to everyone here as well.
Send it to our email.
So yes, I'll send it to the email. If you wrote your email down on that
Yeah, I
sheet
did.
too, I will, yes.
Good.
Okay, so
Thank you very
thank
much.
you so much.
Excellent.
Thank you all. And Morgan, I'm going to stop sharing and I'll send you the link for the recording as well.
Okay, thank you so much.
Okay. Thank you all. Have a good day.
You. Bye.
So should we